Any questions? Yes.
So the quiz seemed to have an error on one of the problems. A quiz question, I don't know if you're aware of it.
No. Keep on.
You're not aware.
I'm not aware.
Okay, so I think it's a form of expression. It says something that, I forgot the specifics, but
You remember? Well, we can pull it up. This was quiz 21, I guess. Questions? Okay, there's a couple of them. Which one? 7. I'm going to have to count. 8, 9, 10. Guess that would be this one here. This one here?
no, wait, no. Line, if we're using a string to show the population order of arithmetic expression. I think that's it.
This one.
So I think the book says interior nodes contain operators.
Right.
And you have the correct answer, interior nodes contain numbers.
Well, but it says which ones are not correct. There's a not in here. Okay, that happens. Okay, other questions?
Do you ever foresee the C?
Yeah? 14C? Yes.
Can you explain that?
Yes. Next question. Do you want an explanation or you just want to know if I can explain it?
14B?
No, I'll explain 14C. Never mind. But the question was if I can explain it. Of course, I can explain it. So, assuming that the follow-on question is now, will you please go on and explaining it? Let's go at 14C. So 14C is not hard, but it is somewhat unintuitive, right? So let's back one up here and go through this. Here where it says for background information, read through P16.9 in your textbook. So the way that we've been talking about linked lists is you have a linked list and it has a pointer to the first node, and that points to a node, and then you have a pointer to the next node, and so on. And so that certainly, has gotten us quite far, but there is a different view of a linked list that's really quite different. And so in that different view of a linked list, And so I'll do it with linked list first, and then we'll migrate on to trees. And in that different view, you think much more abstractly. And you say, there's two kinds of linked lists. There is the empty list, which is often called nil. And then if you have any list at all, then you can construct out of that another list that's often called A colon colon L, where A is an element and L is another list. So every list is either nil or it is a list with a given head A and with a given tail L. So for example, a list would be 1, 2, 3, nil. That's an example of a list. And so in this symbolic view, we're not really interested at all in nodes and stuff. We're simply looking at it as a data structure. And that's kind of a powerful view, because now it becomes very simple to make algorithms. I'll give you an algorithm that computes the length of a list. And now to compute the length of something, I have to tell you what is the list of, what's the length of, well, there's two kinds of lists. There's the empty list, and there's a list that has the form some head, some tail. Those are the only kinds of lists that exist. It has to be one or the other. And so I'm going to say the length of nil is 0, and the length of A colon colon L is 1 plus the length of L. It's a recursive definition for sure. So then when one computes what's the length of, say, 1, 2, 3, nil, then you can see that eventually, if you do the recursive computation, it's 1 plus 1 plus 1 plus 0, or 3. Because 3 times in a row, you strip off something in front of, at the head, and then you're left over with an empty list, and then it's 0. So in particular, there's a programming language called Lisp that, that takes this point of view. And Lisp is actually one of the oldest programming languages in existence. It started, I believe, in 1959 or 1960. And so this has been around forever, and it's powerful and convenient. Working with these lists is actually quite nice and simple. One of the things, though, that's maybe interesting about them is that any computation that you do with these lists, you never mutate the list. There's no way of, if you have a list, and by the way, this list here is usually written in short form as just the list 1, 2, 3. But so these lists are kind of like Java strings. If you want to have the list 1, 2, 4, you have to figure out how to transform one to the other. It's easy enough to transform something in front, but in the back, it's usually some amount of work. So we want to now use our much more limited Java language to imitate something like this. And so whenever in an object-oriented programming language, there's two kinds of ways of doing something. Then we use inheritance or interfaces. So if one says the behavior could be this or the behavior could be that, then that's exactly, I mean, really the key term here is polymorphism. So we would like to say, okay, length is a polymorphic function. When operating on an empty list, it works one way, and when operating on a non-empty list, it works another way. So from an object-oriented point of view, we'd like to say there is an interface list. So these are now classes. There is a class empty list that implements this interface. And there is a class non-empty list that also implements this interface. So now, with the way we would deal with the length method, we would say, fine, length is a method of the interface. There's an implementation length here, and there is an implementation length here. So the implementation here is very simple. It always returns 0. The implementation here is a little bit more complicated, so let me write it down. So, do we have the declaration here? Nope. Do I use implements here? Yes, implements. And I guess I called it the Lisp list here. So I'll do the same thing here. And we have a head. And we have a tail. Now, what's the type of the tail? Now, we're not at trees yet. I'm still at that P69 exercise. Okay, I'll give you 3 choices. Is it node? Is it list? Or is it any list? It's list, right? Because it could be empty or it could not be empty. We don't know. So we have to. Okay. Notice that it's not node. So in a way, these lists are much more elegant because we say that the tail of a list is again a list. Whereas in the what we had before is we always had this icky distinction that you had the list that's the thing that the public was able to touch. And then the list had a dirty little secret, right, that was made up out of icky nodes. And no one ever was allowed to see the nodes because they're so weird. So if one wanted to make a tail of this thing, then one would have to come up with a new list and somehow hook it up with the nodes. Whereas over here, we're just going to say the tail of a list is again a list. And for lists, that's a small win maybe. For trees, that's actually really pretty nice because for trees, we really like to think of the left subtree and the right subtree. But in all of the discussions that you're going to have in chapter 17 is going to say the tree whose root is that node, and we don't always have it as an object of type tree. So this more theoretical way actually makes it a lot easier to talk about these things. All right, so here we are at the non-empty, at the implementation of length, which is what I started out with. So let's implement length, public int length. And so we have a non-empty list, so I know there is a head, and I can simply say return 1 plus tail dot length. Now, when you look at this call here for a minute, notice that tail is never null. Tail might be a reference to an empty list, but it's an object, it's an actual object. And that empty list would, when it's asked now how big it is, it would say, oh, my length is 0. But it's an actual object, it's not the null reference. We've completely avoided any nastiness with null here. And also notice that this call here is polymorphic. tail is a reference to list. It could be an object of one or another implementing class, and the correct one gets picked at runtime. So it's all super object oriented. That's not what we had at the beginning of the semester. And so this is considered, a pretty nice way of setting it up. Why doesn't one always do that? The biggest problem with this approach is that if you want to make a copy and change some of the elements in the middle, then it does get more expensive than with the approach that we've been having, where you can edit the list in the middle. So it's not a suitable solution for everything. But it is a very suitable solution for a lot of things. And as I said last time, with these structural sharing data structures, they're becoming more and more in vogue. So you may see this in, not just in your lifetime, but in the next few years as a more mainstream data structure. So that's lists. What does that all have to do with trees? So clearly with trees, you can do the exact same thing. So now with a tree, we would say, what's a tree? A tree has a root, and it has a left subtree, and it has a right subtree, except a tree might also be an empty tree. And do I call it nil or empty? I don't remember. Let me look at the problem description. Nil. So those are the two kinds of trees that we can have. Now when you follow through how you would implement them, you would implement them in exactly the same way. We have an interface Lisp tree. So you would now have a class empty tree and a class non-empty tree, or maybe any tree. How did I call it? Non-empty tree. I just spelled it out here. Non-empty tree. And now the class empty tree has some methods. What methods does it have? We know what method it has. It has the methods that it inherits from the interface. So what might empty tree say? Imagine this gentleman over there is an empty tree. And we're going to ask him, hey, are you empty?
Yeah.
Yes, he is. Okay. What's your data? No, now you throw an exception. Throw something at me. No. So for all these here, they would throw some exception. Because if you ask an empty tree what the data is, I mean, that's an insult. So they would throw a highly insulted exception, and that's what it is. So now if you're a non-empty tree, so when I ask a non-empty tree, are you empty? Then they would say, well, most certainly not, sir. And when you say, what's the data, then the tree would reveal whatever is in the root. And then when one asks for one of these, it would just hand over those, what the left and the right tree are. Easy. Now there's a few other things that we needed to do. One is to do toString, right? Because some of these things here, like, do we have to do toString yet? For the draft? It says so. That's not fun. How do you know? Oh yeah, here I'm calling toString. Yes. Yes. So you have to do toString, and so the way that I've rigged up toString is that it should give a visual representation that is exactly the same that I'm using in this test here. Notice that in this test, I have a few helper methods. I have this helper method T that takes a root and a left and right subtree and just calls the constructor. And the only point of the helper method T is that it's shorter to say T parentheses than it is to say new non-empty tree. That's the only point of it. I have a helper object nil, and all empty trees really are all the same. If you met two different empty trees at a party, they would act exactly the same. You would ask them, are you empty? They would say yes. If you ask them anything else, they throw something at you. So they're indistinguishable, and so we might as well just have one of them. And so that's the object I have here. So when building up some trees, then you can always do it with this T and the nil thing. There's another helper that says, well, if it's a leaf, then there's no sense in supplying 2 extra nils, and this helper does that. So if you look at the tree, for example, here, let's just draw it really quick. So we're having a root as an asterisk. Then the left subtree is this one here, and we'll come to that in a minute. And the right subtree has a 5, and then it has 2 empties here. And then this one here has a plus, and then a 3 and a 4 and nil, 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 nil. So that's what the tree looks like. So, and you define it with these T's. Now what I say is that when you call toString on it, you're supposed to use the exact same notation. So in the empty tree, oh, actually, here's one weird question. How come toString was not listed in here? I said that you have to implement 4 methods for every one of these 2 classes. But toString is one of them, so it appears that you have to do 5. And yes, you do have to do 5. Why is toString not listed? Yeah? Exactly, very good. So toString is defined in Java Lang object, and so every class has to implement it. And you could put it there, or you could not put it there. It makes no difference. So, of course, if we don't implement it, we inherit a useless toString from object. So you will need to override it for this homework. So let's look at toString. When one calls toString on an empty tree, what should the empty tree answer? Nil, exactly, right? In uppercase. We're done with almost all of the work here. When one calls toString on a non-empty tree, then it needs to work a little bit harder. It needs to produce a T, an opening parenthesis. Then it needs to call toString on the data, comma. Then it needs to call toString on the left subtree, comma, toString on the right subtree, and produce this parenthesis. Except if the left and right subtree are both empty, in which case it has to produce T, an opening parenthesis, call toString on the data, and a closing parenthesis. So I've just, in the oral tradition, communicated to you the pseudocode for toString. That's what we'll all do when there are only computers left and no more paper. So is that enough to get you going for the draft? I think so, right? Yes?
You said in the interface you need to implement 5 methods?
I said that for the homework you're going to need to implement 5 methods, namely empty, data, left, right, and toString. But toString is not mentioned in the interface because you get a free ride with toString since it happens to be defined in the object class.
So it's only 4.
You have to implement 5.
But in the interface it only lists 4 methods.
That's right. I could put toString in there, but I didn't. I didn't have to.
Okay.
That's just, there's a pixel shortage going on, so I try to keep it as short as possible. Other questions? All right, well, let's get going with the lecture, and if there's more time, then we can go back to the homework. Where's my lecture? All right, so all of this here is no mystery. A binary tree is a tree where each node has 0, 1, or 2 children. Now, actually, it's a little bit more specialized than that. If you have a general tree, and a node happens to have a single child, in a general tree there is no notion of whether that is a left or a right child. Whereas in a binary tree, it matters. So if it's on the left versus if it's on the right, these are different trees as binary trees. And so there are lots and lots of applications for binary trees. The book gives a few of them. There's these decision trees where at each time you ask some question, yes or no, and it gets you either to the left or to the right subtree. Should be pretty self-explanatory what these things might be good for. There is these Huffman trees, and we'll talk about them in the next lecture. There is a worked example on Huffman trees, and I thought it was interesting enough, and we have the extra time, so I'm going to spend a lecture on it. Fair warning, the quiz for next lecture, because I couldn't come up with enough good multiple choice questions for Huffman trees, the quiz for the next lecture talks about the lab that you had last week, the scripting lab. And the other reason that I wanted to put extra attention on that scripting lab is that one of the questions in the final will be about that lab. So I want to make sure that absolutely everyone has had a good look at that lab. That is probably the most important lab of all of the labs that you've taken, just in case of your general survival. So for Wednesday, it's not for Wednesday. Yeah, it is for Wednesday. Yeah. As someone asked in Piazza, yes, we do have class on Wednesday, and no one has given us Tuesday off either. So for Wednesday, read that worked example on Huffman trees, and also scan that lab on scripting before you embark on the quiz. Then we'll be looking at binary search trees extensively in the lecture after that. It's very important. And then these expression trees that you've seen, they're also good examples of binary trees, at least if every operator is a binary operator. So if you have something that looks like that, that's clearly a binary tree again. And you have a homework with those. So binary trees are everywhere. They're really important constructs, and we'll be seeing lots of them. There's an important concept with binary trees, namely whether they are balanced or not. So a balanced tree is one that's pretty full. It's not a perfect notion, no. But the tree that you see on the left, the red one, is balanced. Most of the opportunities to fill in contents have been used. That skinny tree on the right-hand side is unbalanced, and the reason that we say it's unbalanced is if you think of it as a scale, you look, there is a lot of heavy stuff on the right, and on the left there's almost nothing. So if it was a scale, then the right hand would hang over. We'd say a tree is balanced if for any child that both of the subtrees are more or less the same. Here, of course, they're a little bit different. Here, they are different, but not completely different. Whereas over here, if you look at these two, they're totally different. Okay, so let's start out with an easy clicker question. We've talked about the height of a tree last time. And now I want to have a binary tree. I forgot to say that here. A binary tree of height h. And what is the smallest number of leaves that it can have? Okay? All right, so when I look at a question like that, I'm not very good with math, so the thing I always first do is I say, well, let me look at an example. Let's say h is 4. So now I have a tree whose height is 4, like this, for example, right? How many leaves does this one have? Yeah. Okay, now, so this way I would get more leaves, right, if I add more of those. So it doesn't look like making it fuller is going to do me any good to find out what is the smallest number of leaves. Well, I could start taking things away. And so what stops me from doing this? That's a tree of height 4, right? How many leaves does it have? 1, right? That's the leaf. That seems pretty small. So shouldn't I naturally choose this one? Let's see what people did. Um, 23% chose 1. Okay. So again, in slow motion, you know, we're not smart enough to do this. Obviously, 77% of us are not smart enough to do it for a general H. So you might as well choose a specific one. You know, choose 3 or 4 or something, and say, you know, how can you make the number of leaves as small as possible? You know, here I have 2 leaves, this one and that one. So scribble up an example on a sheet of paper so you know what the problem is about, and then try to work it. Okay, so let me ask another question though. So I'll make a clicker question 2.5. No, 1.5, I guess. What is the largest number of leaves that it can have? Where's Piazza? So in this case, I'm not going to say 1, right? That's obviously silly. You can have more than 1 leaf. So I'll give as choices h, 2 to the h, minus 1, because I don't have a way of writing exponents on here, 2 to the h, minus 1, and something else. So here we have a tree with height 4, and it has 4 leaves. Can I get 5 leaves? Sure, right? Because I take one of the things that are not quite up to the height and give it 2 children. And now I've traded 1 leaf for 2, so now I have 5 leaves. Can I have 6 leaves? Sure, right? Because I can say, hey, here, now I have 6. Can I have 7 leaves? Sure. Can I have 8 leaves? Sure. Can I have 9 leaves? No, I can't do that, right? Because then the height gets to be more than 4. So it looks like 8 is the max. So let's see. So I'm certainly not going to vote for H because that would be 4. I'm not going to vote for 2 to the H minus 1 because that would be 15. So I'd be tempted to vote for 2 to the H minus 1. And we'll see. And so a lot of people did that, and right now some people are trying to catch up with me, so I'm going to close the poll. So before I did that, I think these two here were evenly favored, but they're different. 2 to the H minus 1, that's the number of leaves. Here in this case, H is 4, and I have 2 to the 3, or 8 leaves. What is 2 to the H with the minus 1 on the bottom? That's exactly right. Thank you. That's the number of nodes in a completely filled tree. And so you will be seeing these equations in the next couple of lectures. All right, so that was that. Okay, so here we have the binary tree implementation. This one here is really, you should think of it as the two-dimensional analog as the linked list that you've been seeing the last several weeks. So we have a node class. The node is just like the nodes of a linked list. So you have something that carries the data element. And now we have, instead of having a node next, we have a node that points to the left and a node that points to the right. The binary tree has a root node that's exactly like a linked list that had like a first element. So think of a binary tree and the binary trees node as just like the same as the linked list, except with one more pointer, with one more reference in each node. And so when you're working with code for binary trees, they often look very similar as the linked list kind of code that you've been learning to love over the last 2 or 3 homeworks. All right, so here we are making a binary tree. It's kind of a softball question here, but let's do it. And so I want to know, what are the leaves of this tree? Oh, oops, now I have to change the choices. Okay, well, here we have an overwhelming answer for option 3. So, and that is in fact correct. So we have Fred on the top. Fred has as a child Barney and wherever this example comes from. And then here we have Wilma. And that's the tree, right? The nulls mean that there are no children there. And so you can see these are the true leaves. So simply writing it up on paper should give you the answer for this. All right, moving on. Now, so here is where trees are a little different from linked lists. Almost all the computations that we've done on linked lists were iterative, that there was some kind of a loop where you would go into the innards of the linked list and do something somewhere. Like, remember that beautiful homework where you had to reverse all of the links that surely no one will ever forget? You had to have a pointer, and then you reversed something, you moved some on, and you did some more surgery on that poor linked list. And so that kind of looping through the nodes of a linked list is very common. With a tree, that's not quite so common. So if let me get a picture up on a tree here. Where did I have one? Like if you look at a tree on the right, like the green tree, there are some algorithms that we're going to be seeing right after Thanksgiving where you need to go to this element. And in that case, we really will be looping and say, if turn left, turn right, whatever. We will be following this path, and it's again a loop. But more often than not, that's not what you're interested in. More often than not, you want to look at all of the nodes in a tree. And so when you look at the tree on the left here, there's no obvious way to loop through here, right? I mean, you can't just go here and then what? Now you're stuck, right? And so the way to deal with the tree is much more often to say, recursively look at the left subtree, recursively look at the right subtree, and then piece that information back together. So almost all the tree algorithms that you're going to be writing are going to have that recursive computation. So here, I'm giving this a good try. So here I'm having a binary tree class, and I want to compute the height of the tree recursively. So here I have my node class. And notice that the recursion always works on the level of the nodes, because the nodes are the ones who have nodes as children. That's why I was saying that the abstract model that you're doing in the homework, was a 14C, is much more beautiful, where the trees have trees as children. Here we always have to go from the trees to the nodes, and the nodes are the truly recursive thing. So the recursive function is on the node level, and then we have a handoff function on the tree level that calls it. And so I have 4 tantalizing options here. Well, let's see what you think. I'm sorry? Did I mess something up? Oh. This is... Okay, I have no idea what I just did. Okay, this is the one I want, right? 22, clicker question 3. Are we good now? Okay, thanks. Interesting. So when I just now looked at the question, some of you may have detected that I was a little dubious about it. I thought there was a fifth option, namely that it would throw a null pointer exception on the empty tree. But actually, if you look at it carefully, that's not true. Suppose the binary tree is empty. In that case, that means the root is null. But we're not calling root.height. We're calling the height of the root. We're feeding in the root here as a parameter. So last time around, we had a bunch of these functions, and it said root.height. And that would have clearly been bad if the root had been null. But instead here, we're feeding it in as this parameter that is explicit. So you have a method of the node class, and it also has a node parameter. So that is different from what we had last time, where we just had a method height that operated on the nodes directly. So let's see what the majority answers here are before I reveal this deep secret. So as the majority, but not the absolute majority, observed, this method here should really have been a static method. This method here does not depend on the contents of the node. This method takes any old node as an explicit parameter, and then it computes the height of the node that was given to it. So there's a difference between calling n.height and height of n. And I want to highlight that difference. So in the first case, when you call n.height, that means you're having a node in front of you, you're facing that node and say, hey, what's your height? And the second one, you say, there is some service, there's a height function, and you can ask that service, here, I'm going to give you a node, tell me what is the height of that node. And so they're subtly different, and one always has the choice to set it up one way or another. You can always switch between the 2 points of view. We like this point of view, where we say n.height. We particularly like it when the call is polymorphic. when depending on what n might be, would be one or the other, which is exactly the situation you have in homework 14C. You have a tree which may be empty or non-empty, and you want the dot to figure out the right thing. But with the nodes, we don't have that situation. There's only one kind of nodes. So with the nodes, there seems to be very little difference between n dot height and height dot n. N dot height is the object-oriented way. Height of n is just, a function. But it turns out that height of n has one major edge. So using a static method, a method that doesn't have an implicit parameter, that doesn't have something in front of the dot, in the world of nodes has a huge advantage, namely what? So why am I making this into a static function? There's a 4-letter answer. No. Right? The 4-letter answer is no, because if n is null and you invoke a method on it, it blows up. If you pass a null to a function, nothing bad is happening. So it makes it easier to write these helper functions that work both with null and non-null references when you pass them as parameters to a static method. And so null is the reason that you will see these static helper methods in the implementation. So we really had to write here private private static int height to make this example correct. What happens if we don't put static? Will it compile? Will it run? I should make that into a clicker question. Let's see. No, I have enough clicker questions. So if we don't make it static, then this call here will not compile. Because when you have a non-static method, you need to invoke it on an object. It would have to say some node dot height. And you don't see that here, so obviously this line would not compile. What about this line here? Would it compile without the static? It actually would. It would mean this dot height of n dot left. And it's kind of bogus. We're not really asking this. We're not asking the current node any question, but it would compile anyway. So anyway, the point is that these helper methods are generally static so that they can deal with null for no other reason. And it is a little ugly that one has to worry about this kind of stuff, and no one really loves it. But the alternative would be to do these more functional data structures like you have in homework 14C, and no one's gotten themselves over to do that yet in 46B. All right. Here we have another one. So you have another implementation of height. And now I did make it static. Over here you see that I made it static. And we have a couple of other options of what might be wrong. So let's have a look at that. All right, so here it says the public height method should have been static. That can't be right, because in a static method you cannot access the root instance variable. Root is an instance variable. You cannot access instance variables in a static method. The method returns the wrong value for every tree. Well, let's see how it does on the empty tree. So on an empty tree, it returns the height of null, and that's 0. Does the empty tree have height 0? Yeah. So that can't have been it. So let's see what most people said. So most people at the next option, it returns the wrong value for every non-empty tree. And that is in fact the answer, because when you look at the math max here, notice it forgot to add the 1 plus, or right. So it computes the max of the left and of the right, which are always 0. So in fact it returns 0 for every tree. That's an easy way to achieve that goal. All right, so this is a good segue into 14b. No, not 14b. Which is one with the expressions? Oh, no. And into 14a. So here you're supposed to count the number of all interior nodes in a tree. So that's a very simple application of this process, right? Because you count the number of interior nodes by looking at the number of interior nodes on the left subtree, and you add to that the number of interior nodes in the right subtree. And clearly this one here was an interior node as well, because it had children. And so there is almost your entire answer. You go to the slide here, and you say, well, in this case it's not math.max. I guess you should go to this slide here, right? It's not math.max, but it is plus, right? Just the sum of them. And it's not height, but interior nodes. It has to be static here. One has to fix that. And then you need to worry about, well, if it was not an interior node, then of course you shouldn't be counting it. And so there's some special case for that. So that seems like a pretty easy one. There was a general question whether homework 14 is just as hard as homework 13. And so when I assigned homework 13, I thought homework 13 was pretty hard. Then last Monday, I said, does anyone have questions about homework 13? No one had any questions. A couple of people said, oh, it seems to be a piece of cake. But it was hard, right? So I think homework 14 is not quite as hard, because 14a is pretty easy, and it gives you the same points as the others. 14b is kind of a classic question. And here, the hard part is to deal with this nasty pattern of these things, right? And that's what I call the prefix. And so if it's easy for you to see some prefixes. Here you see one. And well, actually, what is the prefix? Is the prefix this? Because I didn't tell you, right? So we have a bit of choice. Is it this much? Is it, oops, is it all of this? So what I told you is you should think of the prefix as the CRUD that you need to print before every element of the subtree. So if we look at a subtree like here, this is a perfectly good subtree. Look at this subtree here. If this one had been printed on the top level without CRUD in front of it, we would have printed it as Ann, the left margin would be here, plus minus minus Peter, vertical bar, plus minus minus Savannah, plus minus minus Zara, right? But now we're printing it indented by some amount. And so it seems like every line here, except for the first one, has these 3 vertical bars. But the first line has this thing here, and that is because that points to the root of the tree. Did I give any hints? No. Okay, so that's the hint that I gave, and so I'm going to pretty much leaving it at that. So make up your mind what prefix you want to pass to an, and kind of your choices are: do you want this to be the prefix? Do you want this to be the prefix? Or do you want these 2 vertical bars with the spaces following after to be the prefix? And then you need to design your algorithm accordingly. So I'll give you one possible choice. Maybe these 2 here are the prefix. And now what am I going to do? Now I'm going to print myself preceded by a plus minus minus. First by the prefix and then the plus minus minus. And then I have to print my child. And now I have to print it with a longer prefix, of course. So you print the prefix, you print the root, then you print a new line, I would imagine. Then you print the left child. With some longer prefix. And then you print the right child. With longer prefix. So that's not really pseudocode, of course. That's a storytelling, but it gives you a plan of attack that you could translate into pseudocode. For it to be pseudocode, one would have to say what actually is the longer prefix. And you need to figure that out, of course. But you can do that, and you can turn it into actual pseudocode, and it'll work. I don't think there's any particular rocket science to this. You just need to work through the details. That is an issue that I had. Right now I'm still laboring on the stupid exam, and so that's an issue that I had with pseudocode. So a good number of you did a really nice job, and the pseudocode was much crisper and easier to understand than last time, and so that was good. There's still some number of people who write the pseudocode, the wishful thinking kind of pseudocode, where the pseudocode says what you would like to have happen, and it doesn't explain how that should happen. So always keep that in mind with pseudocode, that at the very beginning, one does write the wishful thinking kind of pseudocode. And the job of a pseudocode writer is then to replace it with something concrete until it gets to the point that really every line of pseudocode can be unambiguously translated into actual code. And it's a process, but it's not finished until you're at that point. The other thing that I wanted to mention quickly about the exam was 2 things. Number one, there was a number of people who on the midterm had, let me show you what they did. So this was the question on how do you find the most frequent something, which is a very common algorithm. So you want to know how to find the most frequent something. And so if you remember from the midterm, there were 2 options. Option number 1 was to sort and to look at adjacent duplicates. So the picture that you would have in your mind was A, B, B, C, 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 D, D. And then you would count how long each of these adjacent sequences was. Oh, what's the big O, by the way? N log n, exactly. And the reason is you pay O of n to make the copy. You pay O of n log n to sort, and then you pay another O n, depending on how you arrange it, to make the traversal. I mean, you can do this in a single traversal, and the O of n log n dominates over the O of n. The second one is actually much better, and that's what it's done in practice. The second one is you make a frequency map. And there was a number of people who wrote me down the map as this. What's wrong about it? It's not a map. In a map, a key has a single value. Right? That's the definition of a map is that every key has one value. And so when you have the keys A, B, C, and D, then the value is the count or the frequency. And so that's what the map is. If for whatever reason you map B and D to the same two, I don't care, but that is what the map is. And so when you have a map, you always need to ask yourself, what are the keys, what are the values? There's some people who try to solve the problem the other way around, where they tried to make the keys the frequencies and the values the A, B, C, and D. Why can't that work? Yeah. Exactly, and that's exactly like what here happens is you can have two letters, the B and D here, that have the same frequency, but that's not legal. There was one person, and I really feel for that person, who recognized that and then made the following map. Where the keys were the frequencies and the values were collections, sets or lists, I can't remember, of the ones with the same frequency. That is a very difficult map to work with, because now suppose that you read another B. Now you would have to find out where the B was, remove it from that set, find the set of all of the ones with length 3, which in this case is not yet existing, in this case add it, and then add it to that set. So that's no good because it ruins the efficiency. So what is the efficiency of the algorithm that we actually had? The black one here. This one here is a very good algorithm. It's O of n, because adding every element is O of 1. And then looking for the largest one is also O of 1. So that means if you ever had to solve a problem like that where you needed to find the most common one, it's very difficult to do this with a linear CS46A style algorithm. You might have had exactly that problem in 46A. It's a common way of torturing freshmen. Say, write an algorithm that finds the most common one and try to do it without sorting. It's even harder. And but with a map, it becomes completely trivial and it becomes super efficient. It's the way to go. It just has to be the right map. All right, that's all I have. So everyone, see you Wednesday.